So here's a question. Here's a question. I have an annulus like this. I have a disk, but it has a hole in it. Okay. Let me call this R1, this R2. This is a disk. The disk has a charge of plus Q, and let's say this is minus Q. Okay? Do you understand the system? Now, the question is, what is the escape velocity? What is the velocity with which I have to throw this charge so that it never returns back? Do you understand the question? So it has to be equal to the potential energy. Like the kinetic energy, yes, has to be equal to potential energy so that it never comes back. Now, what is the potential energy of this system? In short, that is the question. But of course, we will not ask it directly, but we will ask escape velocity. So, what is the potential energy of this system? How can you find it?
So, for rings of the annulus, there is a symmetry. So I will integrate the rings.
Exactly. Very good. So at R, let's say there is dr, okay, and there is dq in that dr. So dq will be the surface charge density times 2 pi r dr, right? What is the surface charge density? Q over pi r2 squared minus r1 squared, right? Because it has a hole in it. Good. Then what is a tiny bit of potential energy here? It's minus kq dq over r, right? Do you agree with this? So,
what is this potential energy? Where is it?
potential energy, this potential energy comes from the interaction of this minus q with this dq.
Is this a point charge inside?
This is a point charge inside, okay, and we are throwing it out of the annulus. Yes. So, what do we have here? K big Q over pi r2 squared minus r1 squared, and I have 2 pi at the top. Just let me know if I miss anything. Yes, I did put the minus. dr, r dr over r. Did I miss anything?
No.
And the integral goes from r1 to r2. Right? So these r's cancel each other out. What do I have? R2 minus R1, right? So U in total, so the whole U is basically negative 2 pi k q. Okay, pi's go away, right? So let me just write 2kq over r2 squared minus r1 squared times r2 minus r1. And this one is, so I can just cancel this one out with the top. And what remains here is r2 plus r1. Right? Turns out to be a very nice, elegant problem. And coming back to the initial statement of the problem, for the escape velocity to be the escape velocity, you need to have m times v escape squared over 2 minus 2k q over r2 plus r1 be 0. Then it will never come back. Okay? You can figure out escape velocity from here. Let me solve another question. If you have any questions about this one, no? No. Here's another question. Let me put the coordinate system first. So I have an x, okay, this is the middle part of the x, and I have a bar here, an infinite bar. This goes to infinity. So it goes to infinity in this direction and in this direction. But between, let's say, these points, should I just remove this one and put it right in the middle? So it goes so. Let me also change this one. Oops, sorry. Yes. So this is x equals to 0, this is x equals to a, this is x equals to minus a, and I have a charge density of rho. First of all, do you understand the system? You do? So the question is, what is E of x? Everywhere you can answer. Like, what is E of x to the left of minus a, between minus a and a, to the right of a? Yes? So, for example, what is E of x for x less than a? Did I have a water bottle, or is it someone else's? I've been drinking it today, but was it yours? No. Yes. So, do you have any ideas? No ideas? Yes.
Can consider the surfaces.
So you want a Gauss surface, right? So you can have a Gauss surface that goes like this. Why? Because you know that electric field will be aligned with x. So if you have a cylinder like this, it will be, the electric field will be perpendicular to here and perpendicular to here, but it will be parallel to the lateral sides, right?
So we have two sides that have
We- We have two sides that have electric field, and over here it's to the right, over here it's to the left. And we can apply Gauss's law. We can say that E times A, and there are two of them, is Q enclosed over epsilon 0. Do you agree?
Yes.
What is Q enclosed?
Rho times volume.
Rho times volume, very good. What is the volume?
2 pi is 1
So it's like
times the height.
it's like this area over here times the distance over here, right? Which is 2a.
2 pi r, 2n.
I mean, if it was r, then it would be pi r squared. But we went with a already. Okay?
Ah,
It doesn't matter. So, rho times 2 times a times area. Did you follow this? Yes? So, 2 times E times area is equal to rho times 2 times A times area over epsilon 0. Turns out that 2 cancel each other out, A cancel each other out. E is equal to rho A over epsilon 0. Okay? Did you follow this?
Hocam, we could have write instead and then cancel, right? Same thing. We just did
We
it right.
yes, we could have written pi r squared. It's not 2 pi r. We are talking about this surface, right?
Mm-hmm.
That's pi r squared. This lateral surface is 2 pi r l, but we don't care about lateral surface because
Parallel.
it's parallel. Electric field is parallel to that one. Very good. So for E less than A, it's rho A over epsilon 0 in the negative I direction, right? And for x greater than A, it is also constant and it's pointing to the right. Right? Yes? Tell me. Why did we do what? So, what we have found here applies only outside because we plotted this surface in such a way that it goes out of this object. We didn't cover all of the bar. We covered only A, the area A. Actually, we only covered this volume over here, right? And that volume is A times 2A. It's the volume is A times 2A, 2A times A. So this. There is no cavity. This is a bar. This is a bar. So now we need to think about what happens inside. All right? So let me draw it again.
Aren't you done with the question?
We are not done with the question. We don't know what's happening inside. We only figured out outside. Do you agree with that?
Yes.
Hocam bir şey sorabilir miyim?
Sure.
Instead of Gauss, can't we just think that it takes of little surfaces together?
You mean, are you going to use sigma over 2 epsilon 0 for each surface?
Yani.
Okay,
So integral alsak.
that's fine. That's fine. That's a very good choice. But where did you get sigma over 2 epsilon 0? You got it with Gauss's law, right? So sometimes there's no escape from it. Well, for this one, I am inside, and let me just draw this symmetric Gauss surface. Remember, this is surface, right, over here, and this distance is x. Let's say this is x, and there is some electric field here that depends on x. So that electric field that depends on x times the area must be equal to rho times 2x times a over epsilon 0. Do you agree with this?
Why we didn't say 2EA? We have again 2.
Exactly. Very good point. It's 2EA. Very good. So we get E equals to rho x over epsilon 0. Right? And this time, you can just simply write it E equals to rho x vector divided by epsilon 0, because it will be pointing to the right when x is positive, pointing to the left when x is negative. Do you see? So this is the value for E for the case when it's between A and plus A, minus A and plus A. Do you have any questions, comments? You see the electric field inside is changing, but outside it stays constant. It is like this. Yes, tell me.
Hocam içindeki surface neden böyle dikdörtgen gibi aldınız?
It wasn't actually rectangle. It looks like a rectangle, this one. This one looks like a rectangle, but it's really a cylinder, but we are looking from the sides. So we don't see the surface. So it's actually a cylinder that looks like this. Yes?
Can you get back to the time-dependent equation we derived for, RC circuits?
Why?
We get those equations from ln by, taking the exponential part
Yes.
on both sides. But did we get the ln's as absolute value of x? Because otherwise the ln would not be defined for minus CE or
Yes.
Q minus CE,
Yes.
because Q will always be less than CE.
Don't worry about it. We did make that
We didn't show the transaction.
Don't worry about it. First of all, there are values for negative ln's. We just
No. We can get negative ln's. Input can't be negative.
Input can be negative, then you get complex numbers. Good morning.
Not in this case.
What?
Not in this case.
Well, don't worry about it, okay? And we are studying for the exam. I will come back to it, I promise. You are not happy, so let me just quickly talk about it. What is bothering you is this.
Integrally alırken absolute
Yes.
alırsak there is no problem.
Don't worry.
We cannot write it without the absolute value.
That's right, but I am okay with this kind of sloppiness. Okay? I don't care. You shouldn't care too. Because you know what you are doing, right? Yes. And there are actual values for negative inputs of ln. You get complex numbers. There is a cancellation at the end of the day. So I feel like I have to move to capacitors, because otherwise I will not be able to talk about them enough. So let me move to this question. Another trick question. And don't bother yourself with energy problems. There is no resistance because it's not that chapter yet, right? So I have some points here, A, B, C, and D. Okay? The question is, if VAB is V0, what is VCD? Do you understand the question?
It can be on midterm, right?
It can be on midterm. That's a fair question. It doesn't have resistance in it. It's just how capacitances work. It is actually from your book, like one of the questions at the end of the book. So how would you approach this problem? So let me just call this part, this is one way of doing it. If this is 0 and this is V0, what is the voltage here?
Isn't it opposite?
Do you understand the question? Yes? You don't understand the question? Yes. So I'm telling you that this point, let's call it 0, and this point, let's call it V0. Is that a fair assumption? I can put potential equal to 0 any place I want, given that I respect the potential differences.
shouldn't the potential it be equal to what? Minus V0. Because it is VA minus.
Okay. Sorry. Yes. So what is potential at C? Any ideas at all?
John, can't you do it giving like AB and stuff to the size of the capacitors and
Yes.
then finding C equivalent?
Yes,
and
yes,
then
yes.
B and then
Yes, like do something. So let's say this is V1 and this is V2. Do you agree that V1 plus V2 is V0?
yes.
What about the charges on the capacitors? Are they the same?
Yes, they are same.
At the beginning, they were all uncharged, so this part of the system is disconnected from the rest. So whenever this one gets, let's say this one gets Q1 minus Q1, this one becomes Q1 minus Q1. Or let me just drop the indices.
John, do we close the...
Not yet.
Ah.
Okay. So before we close it, we have the same charges. So Q over C plus Q over 2C is equal to V0. Q is what? 2 over 3. Help me out here, please. CV0? Yes? Two over 3. It's correct, right? V1 is Q over C, so it is 2 over 3 V0. That's VC, right? VC is 2 over 3 V0. And you can see from the symmetry that VD is going to be 1 over 3 V0. Do you see it from symmetry? Over here, there was a V0 potential, but twice of it ended up on the capacitor while the rest ended here, right? So it's like capacitors and resistances are behaving oppositely. When you have resistances, the potential is distributed proportional to resistances, right? But in the capacitors, the potential is distributed inversely proportional to the capacitances, right? So because of that, this will get less voltage. So VD is one third of V0. So VCD is 1/3 V0. So far, so good? Do you understand this solution? Have I lost you completely? No? Is it super easy? No, but just middle. Yes. Now comes the second part of the question. It's a weird question. This is the switch S, okay? When the switch S is switched on, when it is closed, how much charge flows through it? How much charge flows through switch S when it is closed? Do you understand the question? Well, we will see. I have to calculate. Like, we have to calculate. Do you have any comments here?
Now that we closed the,
Mhm. The switch.
switch, I mean, the point C and point D should have equal potentials,
Very good.
and then you gotta approach the question from there.
There? What?
I mean, you gotta approach the question from there.
Exactly. So this time A, B is here. we still have 0 here and V0 here, but C and D now are connected, so they have the same potential, okay? C, 2C, 2C, C. So what do we do now? Don't worry about the current. There is no resistance. Just think in terms of potential differences, charges. Yes.
We can say that the upper and bottom consistent say Q over C, Q over Q1 over C equals Q2 over 2C.
Okay. So what were the charges before the switch was turned on? Do you can you guess? Like I said this is Q, but is this also Q?
No. because
No.
they are parallel. Before.
Before the so what is Q here? So let me tell you. So Q at the top is 2 over 3 C V0, right? 2 over 3 C V0. How about at the bottom?
İki katı mı?
It's the same, right? 2 over 3 C V0. Right?
It's before, right? After.
It's before. It's before. Yes. So I have minus Q here, plus Q here. Why I did this? Because I was wondering just whether there was a charge balance there or not. Okay. Now the situation is different. Now they are going to have different charges because they have to have the same potential. Yes? So because of the symmetry, look, this is C and 2C, and these 2 points are basically connected. So whenever you have 2 points connected, just giving you some advice here, you can think of them like this. Do you see what I did there? Yes? So what happens is that because of this symmetry over here, like 2cc, 2cc, this point over here will have the potential V0 over 2. Okay? Let me now go back. So I'm now telling you that the potential over here is V0 over 2. The potential over here is V0 over 2. What does it mean? What is the charge over here?
C times V0 over.
Very good. So it becomes C times V0 over 2. On this side it's negative, on this side it's positive. And how about here?
CV0.
CV0 plus and minus. How about over here?
CV0.
Are you sure?
No.
Why you are not sure?
I think it's CV0.
CV0, right? Plus CV0, and here plus CV0 over 2, right? Did you follow all this? So do you see what happens? Like the charge over here in this whole region over here became what? CV0 over 2 plus. Over here, the charge became negative CV0 over 2, right? But before, they were equal, and both of them were 0. Do you remember? Over here it was 0, over here it was 0. Now this much of charge has flown. What is the third version of flow? Flown? It's flown from this switch. Flew through this switch. Are you with me? Okay. So how much charge was transferred? CV0 over 2. That's the answer. What is the message of this problem? You know everything. When I explain you, you understand everything, and it's very simple, right? But could you have came up with that solution? Maybe yes, maybe not. It depends on how concentrated you are and how prepared you are. That's it. All right.
I don't understand why we did like minus plus place of the capacitor. Why we took only that?
Like I thought of this as material. Like over here there is a material, right? This material is not connected to the rest of the circuit. And it has a total charge of 0. Okay?
Because they are, and it's the iron point.
Yes, so this is minus Q plus Q. The charge over here is the total charge is 0. But once they are connected, then in this area, the total charge is no longer 0. It's negative, which means that some of the electrons have been transferred from the top side to the bottom side. All right? Flown. What?
Can you scroll
Up.
up? I'm just taking a picture of the thing.
No worries. So one thing that I also didn't cover that well was the situations where you have capacitor. Let's say I have a capacitor plus Q minus Q not connected to battery. Okay? And I have a dielectric. I have a dielectric that would fit right into this capacitor, but it's not all the way in. So if this is LL over here, this is also LL over here, but only X of it is inside. This distance is X. Do you understand the geometry of this system? So what do you expect? Do you expect this dielectric to be pulled in or pushed out of the capacitor? Pulled in. Why? Because it induces charges, it induces polarization in the dielectric, so it makes this part more negative, this part more positive. Right? Not the very surface, but inside something is happening. So then it pulls it in, right? So let's calculate the force with which it is pulling it in. Yes? Yes. So dielectrics are non-conducting materials. Okay, so we think of them having like when you put a dielectric inside a capacitor, let's say this is plus, this is minus, we assume that inside its electronic structure, rearrange it in such a way that this is more plus, this is more minus, this is more plus. Let me just draw one inside, because like this is more negative, this is more positive, this is more negative, this is more positive. So, yes? So, if you want to pull it out, it wouldn't like that, right? It would like it to be inside. Good. How can we find F?
We need to find W work.
We can find W work, or we can find energy of the system, and the derivative of the energy, the negative derivative of the energy should be the force, right? Do you agree or not?
No, aslında like we don't need to confuse ourselves with the sign each time. We could just use this formula from physics 101, which is delta U plus delta K plus W other equals 0. And,
Okay.
and then we can always determine whether it is minus delta U or plus delta U.
So what is the, yes, okay. What is the energy here of this system?
Q bölü C equivalent. Q over C equivalent.
Q squared over 2C equivalent, right? Does everyone agree? So how do you find C equivalent? We treat them as parallel capacitors. Very good. So C equivalent will be C1 plus C2, right? So you have C1 on this side, let's say, and C2 on this side. What is C1? Epsilon 0 A over D, and A is L times L minus X over D. I didn't give D, so let me give you D. Plus K epsilon 0 times L times X over D. Everybody agrees with this? Yes? So your energy is Q squared over 2 times epsilon 0 L over D times, help me out if I make a mistake, L minus X plus KX. Did I make a mistake? It is fine? Everybody can you check, please? Two comes from here. So I have Q squared over 2 epsilon 0 L, and I have D here, and L plus K minus 1 X. So when X increases, does the energy decrease?
Yes.
What does it mean?
We want X to increase more.
Yes. When X increases, potential energy decreases, which means that the system wants the X to be increased, and that corresponds to X going in, like the dielectric going in, right? Let's find the force. Force is du over dx. I don't want to bother with signs, so I will just go with magnitude, okay? So what is the magnitude of this differential, the derivative of this one? Do you know how to take the derivative of this one? What do you get?
We are taking
Sabitler var zaten.
Let me do it, and you just tell me whether I was successful or not. Yes?
Yes.
So this is the force that you are going to get. Bu kadar.
Çok zor gözüküyordu ama.
Hı?
Çok zor gözüküyordu ama kolay çıktı.
Basit gözüken sorulardan çok biliyorsun.
What?
You should fear the questions that are look simple.
Yes, yes. I totally agree with that. It's a bit harder when you have this connected to the battery.
Hocam, we can't do it with E times Q, right? F equals E times Q.
That's a very good question
I
because
think of it first.
because
Yeah.
the thing is that E is perpendicular here. E is perpendicular, so it's not. And besides, this doesn't have a net charge that would create an F.
It's perpendicular to F. Right?
It's actually, yes, it's perpendicular to F. It's actually quite a complicated system, and you need to consider the fringing effects at the edges. Okay.
I just forget about it.
There is even an article about this, actually scientific article, whether what we do in physics 102 is still acceptable or not. As far as I remember, they ended up saying that it is acceptable. Yes.
Hocam bataryaya bağlı olsa Q'sunun değişeceği için bir sıkıntı mı yaşayacağız?
Yes. When it's connected to the battery,
Öyle bir soru çıkar mı?
the problem will be that as it goes in, it will increase the potential energy. But the potential energy of what? Of the capacitor. Do you remember that Sherlock Holmes stuff? Yes? Okay, let's do it. Where are we? We are here. Add page, add page, add page. So let's look at the case when it's connected to the battery. Then potential is the same always, and you have this thing going in. Let's say this is a distance x. So you should look at the energy with 1/2 CV squared. You see, before I used 1/2 Q squared over C because Q was constant, right? I think even this setting got tired and it's responding slowly. Look, I'm moving it and it's, yes. Tell me. Okay, very good question. So why did we take C1 and C2 to be parallel, right? You take C1 and C2 parallel when they are like this. Like, let's say K1, K2. Okay, then it's parallel, like this. This is parallel. And when they are like this, it's in series. Okay? Just bear with me a few more minutes. This time the energy seems to be increasing, right? Because as you put the capacitance inside, the dielectric inside, the capacitance will increase. So it will be, U will be 1/2, help me out, epsilon 0 L over D times L plus K minus 1 X. I will. Do you see that the energy is increasing? as x increases. Do you see it?
Yes.
But there is a catch here. The catch is that we are not including the potential energy of the battery. Okay? So this is just the capacitor. If we include the battery, what happens with the battery? The energy decreases. How much it decreases?
This much.
Did you say this much? That was funny. So it increases with respect to the charge it gets, right? So energy of the capacitor can be treated as Q times V. Actually, negative Q times V.
Why?
Did I say decreases?
Yes. Is it discharging?
No. If I say decreases, it is decreasing because we are taking out charge from the battery. Why? Because the charge over here is increasing, right? Q equals to C times V. And C is increasing, so Q is increasing in the capacitor, which means Q is decreasing in the battery. So the battery energy can be written as minus Q times V, which is minus CV times V, which is minus CV squared. So the total energy will be capacitor plus the battery. Oops. This will be the total energy, and the total energy will be exactly the negative of what you get for the capacitor. Hence, total energy will decrease when X increases. So it will still pull it in.
Same thing.
The same thing as before.
Projects.
But force is different in this case. Force is different. Do you see why? Let's calculate force. U total is negative of this, right? 1/2 epsilon 0 L over D L plus K minus 1 X V squared. So take the derivative du over dx, and I'm just interested in the magnitude. What do I get? 1/2 epsilon 0 L over D times K minus 1 V squared. I get a different expression for the force. Do you remember the previous expression? The previous expression was like this.
Actually, this time it's not dependent to X.
Actually, this time it's independent of X. Exactly. Do you see it? Okay, good luck in the exam.
Thank you.
Yeah, çok sağ ol.
Thank you. Take care.